Welcome to another session of our reading group. Today there aren't many people, it's just Tobias and me. Should we... Well, we'll give a couple of minutes and see if anybody else joins. In the meantime, I can do the usual setting up of pop-up chat. There we go. We can put the link. And there we go. And I can see where we were. I think, if I remember correctly, is this working? Yes. We finished talking about the idea of properties as ordered, of quantities as ordered properties, and we were ready to basically start thinking about references as the thing that we allow, that we have when we are setting up measurement scales to be able to define this before and after in terms of experimental stuff. Okay, I think then it's just I'm still behind setting up everything here. Okay, so the order of reading is Tobias and then Alina. I'll keep an eye if anybody else joins, otherwise we just start.
Okay. References and experimental ordering. In the previous section, we have characterized what a quantity is and how it relates to an experimental domain. But as we saw in the first chapters, the possibilities of domain are not objects that exist a priori. They are defined based on what can be verified experimentally. Therefore, simply assigning an ordering to the possibilities of a domain does not answer the more fundamental question: how are quantities actually constructed? How do we do it in practice? Create a system of references that allows us to measure a quantity at a given level of precision. What are the assumptions we make in that process?
In this section, we construct ordering from the idea of a reference that physically defines a boundary between a before and an after. In general, a reference has an extent and may overlap with others. We define ordering in terms of references that are clearly before and after others. We see that the possibilities of a natural ordering only if they are generated from a set of references that is finable. We can always find finer ones that do not overlap, and for which before or and after are mutually exclusive cases. The possibilities then are the finest references possible.
So the theorems here to prove are quite involved, so we're just going to look at the definitions and the main outline of the proof, because we're not going to have, I don't think it makes sense to go through that.
We are by now so used to the ideas of real numbers, negative numbers, and the number zero that it is difficult to realize that these are mental constructs that are, in the end, somewhat recent in the history of humankind. Yet geometry itself started 4,000 years ago as an experimentally discovered collection of rules concerning lengths, areas, and angles. That is, human beings were measuring quantities well before the real numbers were invented. So how does one construct instruments that measure values?
To measure position, we can use a ruler, which is a series of equally spaced marks. We give a label to each mark, for instance, a number, and note which two marks are closest to the target position, for instance, between 1.2 and 1.3 centimeters. To measure weight, we can use a balance and a set of equally prepared reference weights. Balance can clearly tell us whether one side is heavier than the other, so we use it to compare a target with a number of reference weights and note the two closest, for instance, between 300 and 400 grams. A clock gives us a series of events to compare to, for instance, Earth's rotation on its axis or the ticks of the clock. We can pour water from a reference container into another as many times as are needed to measure its volume. In all these cases, what actually happens is similar. We have a reference, for instance, a mark on a ruler, a set of equally prepared weights, a number of ticks of a clock, and it is fairly easy to tell whether what we are measuring is before, that is shorter, lighter, sooner, or after, that is longer, heavier, later. The reference. Oh yeah, before or after reference, yeah.
Note that determining whether the quantity is exactly equal to the reference is not as easy. The mark on a ruler has a width, the balance has friction. The ticker for a clock will last a finite amount of time. That is, the reference itself can only be compared up to a finite level of precision. This may be a problem when constructing the references themselves. How do we know that the marks on our ruler are equally spaced, or that the weights are equally prepared, or that the ticks of our clock are equally timed? It is a circular problem in the sense that, in a way, we need instruments of measurement to be able to create instruments of measurement. Yet, even if our references can't be perfectly compared and are not perfectly equal, we can still say whether the value is well before or well after any of them.
To make matters worse, the object we are measuring may itself have an extent. We are measuring the position of a tiny ball. It may be clearly before or clearly after the nearest mark. It may also be partly before, partly on, and partly after. One may try to sidestep the problem by measuring part of the object, say the position of the center of the mass or of its closest part. But this assumes we have a process to interact with only part of the object, and that part can only be before, on, or after the reference. It may be a reasonable assumption in many cases, but we have to be mindful that we made that assumption. Our general definition will have to be able to work in the less ideal cases.
In our general mathematical theory of experimental science, we can capture the above discussion with the following definitions. A reference is represented by a set of three statements that tell us whether the object is before, on, or after a specific reference. To make sense, these have to satisfy the following minimal requirements. The before and the after statements must be verifiable, as otherwise they would not be usable as references. As the reference must be somewhere, the on statement cannot be an impossibility. If the object is not before and not after the reference, then it must be on the reference. If the object is before and after the reference, then it must also be on the reference. These requirements recognize that in general, a reference has an extent, and so does the object being measured.
You can compare the extent of two references and say that one is finer than the other if the on statement is narrower than the other, and the before and after statements are wider. This corresponds to a finer tick of a ruler or a finer pulse in our timing system. We say that a reference is strict if the before, on, and after statements are incompatible. That is, if the three cases are distinct and can't be true at the same time. Before we go to the definition, I do have like a quick question.
Yeah, go ahead.
So this idea of references, when we say they are the finest possible, does it mean like at current time with our current methods?
So a reference will have its own resolution. So you are going to have references at all the refractions. So the idea is that suppose that you have a tick of a clock, right? Then that tick will have a length in time itself. So you're going to be able to say that the event happened completely before the tick of the clock. It happened completely after the tick of the clock, happened only when the clock was ticking, or it happened a little bit before and also on, right? All these ideas that you're measuring, you're comparing things that have an extent.
Yeah, like if we can go up to like the start of this section.
Yeah.
Because maybe I misread.
Maybe you're talking about the possibilities, the finest references possible.
Right.
Yeah, that's what I meant. Like, we see the possibilities of a natural ordering only if they are generated from a set of references that is refinable. You always find finer ones that do not overlap and for which before or and after are mutually exclusive cases. Possibilities then are the finest references possible. This is the possibilities, not the references themselves. Yeah, I got confused there.
Yeah, so a possibility is a special reference. It's like the ideal thing. So when you say, the 0 seconds, that's an infinitely precise reference where you have before the 0 seconds, after the 0 seconds, and in principle you have at exactly the 0 seconds, right? And you can't have a reference that it's finer than that.
Yeah, and then these statements that are for references with a width are just like these conjunctions of multiple possibilities. Yeah, thank you.
Yeah. And so the idea is we're going to start with things that are finite as usual, and then we have to find these infinitesimal. And so we have to find the conditions. So now we have all the reference of other possible, given, let's say, by all possible clocks, and none of these will be possibilities because all of them, each clock will last some time. And so when we put them all together, we say, okay, if we get all this bag of references, when can we say that we have the real numbers?
Mm.
Okay. A reference defines a before, an on, and after relationship between itself and another object. Formally, a reference R is a tuple of 3 statements such that we can verify whether the object is before or after the reference, meaning B and A are verifiable statements. Yeah, I forgot to say we call this the BOA for before, on, and after.
Yeah.
The object can be on the reference, so O is not the impossibility or not equivalent to it. If it's not before or after, it's on the reference. Not before and not after implies on, I guess.
Yeah.
If it's before and after, it's also on the reference. So B and A also imply O. A beginning reference has nothing before it. That is, before is equivalent to the impossibility. An ending reference has nothing after it. So after is impossible. A terminal reference is either beginning or ending. Then the corollary, let BOA be a reference. Then B or on before or after, or no, before or on or after is certain. So either of them has to be the case. Okay. Then next definition, a reference R1 is finer than another reference R2 if the before is wider than the first before is wider than the second one. The on is narrower and the after is again wider.
Yeah. So you're
So
basically
they come in
shrinking the.
almost,
Yeah, exactly.
the left and right becomes wider and the center becomes thinner. Okay. Narrower. Corollary, the finite relationship between references is a partial order. It's a partial order. Not all of them are related.
Right.
But we need reflexivity, anti-symmetry. If one is narrower than the other, then it's not the other way around. Okay, transitive makes sense. Okay. I will just finish this block. A reference is strict if it's before, on, and after statements are incompatible. Formally, we have this tuple such that B and A are incompatible, and on is exactly not before and not after. Otherwise, we call it loose. Remark, in general, we can turn a loose reference into a strict one. The on statement can be made strict by replacing it just with by definition. It's not A and not B. This is possible because O is not required to be verifiable. The before and after statements would need to be replaced with statements like before and not after, which are not in general verifiable because of the negation. Could we run into an issue that the on statement becomes impossible as well?
Let me think. Can it become impossible? It shouldn't. Can it become impossible?
If you define it as like not before and not after.
Let
I
me
mean, it would be
think.
another thing that can go wrong.
So then we would be saying
Like this will be the case only if the types of objects you are measuring always have a width that is larger than the width of the reference. Because then no matter where you put it, you always have a little bit before and a little bit after.
yeah, I think you're right. That could become an impossibility. Yep, thank you. I'll make a note of it. Okay. Okay, you can go on while I make a note.
To measure a quantity, we'll have many references, one after the other. A ruler will have many marks, a scale will have many reference weights, a clock will keep ticking. What does it mean that a reference comes after another in terms of the before and after statements? If reference R1 is before reference R2, we expect that if the value measured is before the first, it will also be before the second. And if it is after the second, it will also be after the first. Note that this is not enough, though, because as references have an extent, they may overlap. And if they overlap, one can be after the other. To have an ordering properly defined, we must have that the first reference is entirely before the second. That is, if the value measured is on the first, it will be before the second, and if it is on the second, it will be after the first.
Mathematically, this type of ordering is strict in the sense that it defines what is strictly before and strictly after. It does not define what happens in the overlap in between cases. One may be tempted to define the order based on how the references overlap, but that requires refining the references, and in the end, it means we're defining an ordering on those refined references, not the original ones.
Definition 3.22. A reference is before another if whenever an object is found before or on the first, it cannot be on or after the second. Formally, R1 is lower than R2 if and only if B1 or O1 is this meant not compatible or
incompatible.
Yeah, this B1 or O1 is incompatible with O2 or A2. Proposition 3.23, reference ordering satisfies the following properties. Irreflexivity, so not R narrow. So this lower than is ordering, right? Or am I R? So this is R before R?
Yeah, so R is not before R.
Okay. And then transitivity, if R1 is before R2 and R2 is before R3, then R1 is before R3.
Yeah.
And is therefore a strict partial order. Shall I go through the proof or shall we move to the
No,
corollary?
we just go to the
Okay.
corollary.
Corollary 3.24, the relationship R1 is before or on R2, defined to be true if R1 is before R2 or R1 is on R2, is a partial order.
Yeah, so we make it the order no squares by just adding the equality back.
Okay.
As we saw, two references may overlap and therefore an ordering between them cannot be defined. But references can overlap in different ways. Suppose we have a vertical line 1 millimeter thick and call the left side the part before the line and the right side the part after. We can have another vertical line of the same thickness overlapping, but we can also have a horizontal line, which will also at some point overlap. The case of the two vertical lines is something that, through finding finite references, can be given a linear order. The case of the vertical and horizontal line instead cannot. Intuitively, the vertical lines are aligned with while the horizontal and vertical are not.
Conceptually, the overlapping vertical lines are aligned because we can imagine narrower lines around the borders, and those lines will be ordered references in the above sense. Each line will be completely before or after without intersection. This means that the before and not after statements, when references of one reference are either narrower or broader than the before and not after statements of the other. That is, alignment can also be defined in terms of narrowness of statements.
Note that if a reference is strict, before and after statements are not compatible, and therefore the before statement is narrower than the not after statement. This means that given a set of aligned strict references, the set of all before and not after statements is linearly ordered by narrowness. As we saw in the previous section, this was a necessary condition for the possibilities of a domain to be linearly ordered, and therefore aligned strict references play a crucial role.
Does it make sense intuitively?
So I want a linear order. Everything needs to be related to everything else. And then I want it to be strict, and then I can just move my reference point kind of, and it's going to be naturally ordered by narrowness. Like I focus on the interval minus infinity to my reference point.
Yeah.
And it's going to be, well, it's going to have a sharp edge, I guess, because it's strict. And then everything is related to everything else because the references are aligned, and then I get a linear order. I think that kind of makes intuitive sense.
And again, there is always this trick that you're flipping the after to be not after, and that inverts the order. And then all those things have to be set so that sort of keep increasing.
Okay.
But just like when we say given a set of aligned strict references, instead of all before and not after statements, we mean like statements like before R1 and not after R2, or are those excluded?
Right, so you would have a before one and then not after one, right?
Yeah.
And then you want these two. So if they are strict, these are automatically ordered by narrowness. So this is going to be narrower than this, because if it's before, it's not after.
Right. So it's always on the same reference.
Right. And then we want to essentially to extend this idea that if it's before one, it's not after one, in between references. And that's what's giving us an alignment. So if we basically take B1 and B2, then either B1 implies B2, so B1 is narrower than B2, or B2 is narrower than B1.
Okay. Yeah. Yeah, that makes sense.
Or both if they're the same. But
Yeah. Okay. Definition 3.25. Two references R1 defined as a tuple B1 O1 A1 and R2 defined as a tuple B2 O2 A2 are aligned if for any S1 that belongs to either B1 or not A1 and S2 is an element of B2 or not A2, we have S1 narrower than S2 or S2 narrower than S1, as an R of references is aligned if every pair of references is aligned. Okay. Proposition 3.26. Let R be, this is the set of all references, right? A set of all tuples indexed on I, with I being in that index. Cool. Be a set of aligned strict references. Let be also a set of before relations, and be A being a set of after relations with the same kind of indexing as the R. Let these be respectively the sets of before and after statements. Then the set B, which is B sub B, union not B sub A, is linearly ordered by narrowness. Is that union or is that intersection? I'm not remembering intersection.
no, that's a union, yeah.
It's a union, okay.
Yeah, so
Yeah,
we're
so that
basically
union is linearly
taking,
ordered by narrowness.
yeah, so you take all the befores, all the not after, and they are linearly ordered.
Yeah. I think it's just extending that relation. Yeah.
Yeah.
So the proof we don't read.
Yeah.
Proposition 3.27, let R1 be the tuple B1 O1 A1 and R2 the same things but with number 2. Let these be two references. If R1 is narrower than R2, then B1 is narrow. No, this was before, sorry.
This is before, yeah.
Yeah, I get confused sometimes. If R1 is before R2, then B1 is before or on B2. A2 is before or on A1, and B1 is before or on not A2, and not A1 is before or on B2. Therefore, the two references are
Okay,
aligned.
so this is narrower. So B1
Narrower.
is narrower than B2, A2 is narrower than B1, and so on. And so basically we are verifying that the references are aligned.
Ah, right. Yeah. Right. The B's and not A's are about narrowness. Yeah.
Yeah, so this is
Comparisons of
basically,
references. Yeah, because you're comparing the before and the not after of different references. Yeah.
yeah. So the idea is before we just defined, when a reference was before another, but that's kind of too strict of a condition to say I have references that are all aligned because you might have this overlap. So now we basically figured out, okay, what aligned means is this relationship between the before and after, and then we go back and verify that the definition that we had for one reference before another agrees with the notion of alignment, so that if you have a reference that is before another, then they are aligned.
So we kind of defined aligned for two references, which just means one is before the other. And now we extended the definition to arbitrarily many sets arbitrarily many references, and we just check
Yes.
that the original definition is compatible. Okay.
Yeah.
Right. Proposition 3.28. Let R1 be the tuple ones, R2 the tuple with twos. These are two strict references. Then R1 is before R2 if and only if not A1 is narrower than B2. Right.
So this is a simplifying condition. Again, when things are strict, you only need to check the before and after, and you're done.
Yeah. Definition 3.29. A reference is the immediate predecessor of another if nothing can be found before the second and after the first. Formally, R1 is before R2 and A1 is incompatible. Well, is this incompatibility? Yeah, because this is two references. Yeah, I'm blanking here. Is this incompatibility?
Yeah, this is incompatibility. So there's
Okay,
nothing that it's both after the first one and before the second one.
right. Nothing after.
There's
Yeah,
nothing in the
yeah,
middle.
makes sense. Yeah, and A1 is incompatible with B2. References are consecutive if one is the immediate successor of the other. Yeah, that makes sense. But we defined immediate predecessor. You imagine that, like, are we also taking here that the immediate predecessor of R1 is also implies that R1 is the immediate successor of the previous one?
Well, we don't know at this point what's before. We know that R2 is going to be the immediate successor of R1, right? But we don't know like whether you always have these immediate predecessor, immediate successor. It's something that you find out later. Like for example, if we have real numbers, then references or integers, you would have immediate predecessor, immediate successors. Instead, when we have the real numbers, one of the points is that you're never going to have an immediate successor and immediate predecessor. That's exactly how
Right,
you would actually characterize actually the real number.
right.
And something like the rationals, you're gonna see that there is a mix. There are some that have immediate predecessor and immediate successors, but not always.
Yeah. Then proposition 3.30. Let R1 being the tuple with ones and R2 the tuple with twos. These be two references. If R1 is immediately before R2, then B2 is this is equivalent, right? The B2 is this equivalent statement to not A1. So this one is immediately before. To say that something is before R2 is the same as saying that it's not after R1. I'm not sure I understand this. I mean,
So these are just equivalent characterization to when we have immediate predecessors for strict references. So if you have two references and then you have that R1 is immediately before, so it's the immediate predecessor. If saying that it's something is before the second is saying that it's not after the first.
yeah. Because the first is before the second, and we're not saying that they overlap here. Yeah. So sorry, I got confused there because of the non A1.
Yeah.
Okay,
And
proposition
then
3.31. So
so
that
this is
yeah.
okay. So the point is that this you can invert. So this relationship only goes one way. Like if R1 is immediately before, then you have this. And if R1 and R2 are strict, then you can go backwards. That if this is true, then R1 is immediately before R2.
Oh, so one is conditional and the other one is biconditional.
Yeah.
Yeah. Okay, that's cool.
Yeah, and this is essentially one of the reasons why you need the strict references, because otherwise you can't construct this ordering.
Mm.
Can I think of this negation of after as like taking the complement of a closed interval, getting like an open interval? Like
The
I get
negation
like
will give you the closed interval. It's the opposite.
I start with like open interval
Yeah,
from here to plus infinity. I
yeah,
take the complement, I get minus infinity, and then closed interval. Okay,
yeah.
good.
So, but remember, that's what we want to find,
Sure.
right? We don't know that these will map to that, so we need to construct something, say, with the reference. Oh, I can look at before, not after, and then we'll find that those are with sufficient conditions. That's what's going to be. So if the
Yeah,
references are not strict, for example, then these intuitions fall apart.
yeah. I just want to know what the goal is.
Yeah, yeah.
Uh,
The goal is to find that those are open and closed sets. Yes,
yes. If we
intro,
have
of
a
course.
set, if we have a set of references, we can generate an experimental domain by using the before and after statements as the basis. More specifically, we can take all the before statements and generate the before domain dB, and all the after statements and generate the after domain dA. If the references are all strict and aligned, the set D, union of dB and negation of dA, of all the before and not after statements will be linearly ordered by narrowness. We recognize this as the first requirement of the domain ordering theorem 3.16.
Let's go back to this. Can I click? Yes. So if you guys remember, these were the three conditions that if we had a domain, it's naturally ordered. So you can say that the possibilities are ordered, and there is an order there with the order topology. The first thing is that we need to be able to take the domain and see it as the combination of two domains, such that if you take the before domain and the not after domain, these are linearly ordered by narrowness. Right? So now this is actually what we are gonna find here. So that we start reproducing those requirements.
Definition 3.32, let R be this set of before, on, and after relations. So it's a set of references. Yeah, be a set of references. Let BV be the set of all before statements, and VA be the set of all after statements. The experimental domain D generated by R is the one generated by all before and after statements, BB union BA. The before domain D sub B is a domain generated only by the before statements BV, and the after domain DA is the domain generated only by the after statements VA. Okay. Yeah, okay, so yeah, BA was it was a set of after statements. For a moment there I thought it was before statements as well, but that's just me being a bit distracted. Definition 3.33, let D be a domain generated by a set of references R. A reference R equals BOA is said to be aligned with D if B is an element of B and A is an element of DA. So the before of this particular reference is in the domain of the before statements, and the after of that particular reference is in the domain of the after statements. Then proposition 3.34, let D be an experimental domain generated by a set of aligned strict references R, and let D be the union of DB and not DA. Then this relation is linearly ordered. D with not with narrowness. Yes, linearly ordered
Yeah,
with respect to narrowness.
it's better.
Yeah.
So here the idea is that we start with a set of references, right? And these references start having a set of befores and after. But then we can close these before and afters by using ands and ors. and that allows us to generate new references. So, for example, imagine that I have before, actually, it would be better to say after 3, after 3.1, after 3.14, after 3.141, and so on, right? So you get all the finite references, like the let's say the fractional references that are always before pi, and then you do an and. No, I have to do ors. Sorry, I have to do the other one. You need to do the or, so you say before 3. What is it? I'm still doing the end. Now the disjunct. I need to be able to do the or. So if it's before 3 or before 3.1 or before 3.14 or before 3.1.41, right? So you make all these ors together, and then it's going to be before pi. And so now you can construct the reference before pi by doing the disjunction of all the the approximations. So you can imagine that inside here, inside with the reference that you're given, you're only given the references that are that have finite precision, but then you can construct the sort of the infinite precision by the OR. So that would be the difference between this, the sort of the sets, the before statements that you get from the references, and the one that then you can construct from the domain.
How close is that to Dedekind cuts? Isn't that like the set
It,
of all the
it,
open
it would be
sets
Dedekind cuts.
before or something like that? Okay.
Yeah, it's exactly that. So it's just that they're constructing a different way because we don't have the points. So the Dedekind cuts start with knowing, let's say, the rationals, and then you construct the cuts. We don't know the rationals. We start with sets, and so we have to
Yeah.
construct the sets themselves, and then say, aha, these are the points. But then those are going to be Dedekind cuts of all the other points, essentially.
Yep. Okay. Having a set of aligned references is not necessarily enough to cover the whole space at all levels of precision. To do that, we need to make sure that, for example, between two references that are not consecutive, we can at least put a reference in between. Or that if we have two references that overlap, we can break them apart into final ones that do not overlap, and one is after the other.
Is this just like the condition that they should be refinable?
Yeah, that's what we're going to define here. Like we need to define what it means to be refinable.
Okay. We call a set of references, oh yeah, first sentence. We call a set of references refinable if the domain they generate has the above mentioned properties. This allows us to break up the whole domain into a sequence of references that do not overlap, are linearly ordered, and that cover the whole space. As we get to the finest references, their before statements will be immediately followed by the negation of their after statements, since there can't be any reference in between. Conceptually, this will give us the second and the third condition of the domain ordering theory.
Yeah, this is hard. So let's these definitions are a handful. So let's go through them slowly.
Okay. Let D be an experimental domain generated by a set of aligned references. The set of references is refinable if given two strict references, R1 and R2 aligned with D, we can always find an intermediate one if they are not consecutive. That is, if R1 is before R2, but R2 is not the immediate successor of R1, then we can find a strict reference R3 aligned with D such that it's in between. Okay. And I guess we also need, it's like an and. The second thing also needs to be true. Refine overlapping references
Mhm.
if one is finer than the other. That is, if O2 is strictly narrower than O1, we can find a strict reference R3 aligned with D such that O3 is narrower than O1 and either before 3 is equivalent to before 1 and R3 is before R2 or after 3 is equivalent to after 1 and R2 is before R3. Okay, yeah, there's so many cases.
So the idea is that you have O2 that is narrower than O1. So your on2 is smaller than O1. You need to be able to cut that, right? So that you are going to put something in between the O1 and O2,
Mhm.
right? But you are not going to be able to have since you know R1 and R2 are not one before the other because there is this overlap that cannot, right? You need to be able to cut either on one side or cut on the other side. So you
You always
basically,
you had a picture that you always, at least on your slides somewhere.
yeah, I like this really, all of this would probably need pictures. Let's say if I had some, you know, volunteer to go through and add pictures, this would be, it would be a lot easier. But the point should be that you see O3 is still smaller than O2. So if you imagine O1, O2, and O3 of sets, this O2 is a strict subset of O1, and O3 it's another subset of O1 that is not going to overlap with O2.
Mhm.
And it's not going to be overlapping with O2, and you need to be able to put this R3 before R2 or after R2.
Mhm. Okay. So at
So
the end
this
of the
would,
day, you will end up with two on statements that
yeah,
are incompatible,
yeah,
but they're both narrower than O1.
O1, yeah,
Okay. So you split O1 in two distinct things
yeah.
in any order, but yeah, okay.
So if you have one thing that overlaps with another, you can take the bigger thing and split it into pieces and recover the order.
Yeah. Okay.
There might be a better way to state an equivalent condition that it's a little bit nicer. This is the best I could do. Like this, the first part is a lot nicer to write. This one is a lot trickier. But you know, it's, whatever other equivalent, whatever other condition is going to be something equivalent to this.
Okay. Proposition. Let D be an experimental domain generated by a set of refinable aligned strict references. Okay. If B1, B2 in DB such that B1 is strictly narrower than B2, then there exists an A in DA such that B1 is strictly narrower than not A, which is narrower than B2. Okay. So if there's strict narrowness, I can fit something in between in that way.
You can put another hour after in between. Yes.
Okay. If A1, A2 are in DA such that the negations negation of A1 is strictly narrower than negation of A2, then I can put a B in between. I assume that's just the same. You just flip everything.
Yeah.
Okay. If A1 is in the A and B2 is in the B, such that not A is strictly narrower than B2, then there exists a B in the B and an A in the A, such that I can I still have not A1 narrower than B, which is strictly narrower than negation of A. Okay, I can stick two things left and right, kind of.
Yeah.
Okay. Okay. Then another proposition. Let D be an experimental domain generated by a set of refinable, aligned, strict references. Then all elements of D are part of a pair SB, not SA, such that SB is in the B, SA is in the A, and not SA is the immediate successor of SB in D, or SB is equivalent to not SA. Moreover, if statement S in D has an immediate successor, then it is in DB.
Yeah, it's a before statement.
Okay.
So
Yeah.
the whole idea is that this allows us to see all this ordering of the before and not after at things that are tied together, which is before, not after, before, not after, before, not after. And all these pairs are always together and they're either the same thing or they're different. And that would be where they put the points. Like the point would be in between the before and then not after, which is an immediate successor. So the point 0 is effectively before 0 and not after 0.
Mm-hmm. Yeah.
Right. So all those pairs, when you do the sort of the thing that remains in the middle, those are the points.
Yep.
And I think, in fact, yeah, and the next thing is going to be the theorem.
Okay. The reference ordering theorem. An experimental domain is naturally ordered if and only if it can be generated by a set of refinable, aligned, strict references. Mm-hmm.
Right, so that's basically it. So we have these with set of strict reference. We can align these before and not after, and then these pairs of befores and not afters are the actual points. And yes.
To recap, experimentally we construct ordering by placing references and being able to tell whether the object measured is before or after. We can define a linear order on the possibilities and therefore a quantity only when the set of references meets special conditions. The references must be strict, meaning that before, on, and after are mutually exclusive. They must be aligned, meaning that the before and not after statement must be ordered by narrowness. They must be refinable, meaning when they overlap, we can always find finer references with well-defined before-after relationships. If all these conditions apply, we have a linear order. If any of these conditions fail, a linear order cannot be defined. Let me just finish because the next one is very short. The possibilities then correspond to the finest references we can construct. We can construct within the domain. That is, given a value Q naught, we have the possibility, the value of the property is Q naught, and we have the reference, the value of the property is less than Q naught as a tuple, that statement, and the on statement, the value of the property is Q naught, and the after statement, the value of the property is more than Q naught. Yeah.
And next, I don't think we're going to be able to do this today. We should probably stop. So next, it's basically finding when this ordering corresponds to discrete quantities or continuous quantities. And those two things are a lot easier. Like the proofs of those pieces are much smaller. So the hard bit is to prove that you have an ordering, and that's where you have a really heavy assumptions. But then once you've done that, finding the continuous quantities or the discrete quantities, it's very easy.
So since the goal is somewhat to get to the reals, or I mean, at least I would really want to see how we get the reals.
Yeah.
We justified an order, uh, making it like the step from rationals to reals is making uh completing the order in a sense. Like yeah. But I think if I remember correctly, the axioms of the reals, there is one part which is like the that makes it a field, like addition, multiplication, and then
We don't have that. This is
okay,
purely topological, right? It's only on the ordering. We don't have a notion of distance, so
yeah,
addition
okay.
we don't know, scalar multiplication we don't know.
So to get all the details of the reals, I would need to know what it means to like add masses or something like that, to have
Yeah,
an addition and stuff like this.
yeah,
And I mean, yeah, we would have to pick a unit as well to really get the reals
yeah,
and stuff like this. But
yeah,
that would that's the only thing that's missing, right? I think we need addition multiplication to make it a field, and then it has to be ordered, and then it has to be complete, and then I think we all exactly get the reals.
right. But
Is that it?
the point is that getting the reals is just the order. Like the fact that you have, so if you think, if you have a nonlinear map between the reals, you're still preserving the ordering or the reals. You don't preserve the addition, the multiplication, and all that,
Yeah.
right? So the characterizing the reals as an ordering is much more basic and much more fundamental than characterizes as a field. And
Yeah.
when we do things like coordinates in physics, we are really characterizing the reals as an ordering, not as a field, because otherwise we wouldn't allow nonlinear change of coordinates.
Yeah. Okay.
So what we're getting here is the real as an ordering and with the correct topology. And
Yeah.
the cool thing is that this construction essentially gives you the reals directly. It doesn't really give you the rationals. The rational would be a lot harder to justify in terms of references and stuff like that.
Because it's probably heavily tied to the field properties. Like it's
No,
closed under addition, multiplication, and taking inverses and all of that, or not?
no, it's not because again, topologically, the rationals have holes, right? So
Mm.
if you imagine the set, before zero and after zero, like those
Mm.
two sets, there is something in between.
Yeah.
If you take the set before pi and after pi, there is nothing in between.
Yeah.
When we construct the topology in this way, right? Because the topologies are closed under union, you're automatically getting limits like that. So if you say at some point, I want that between two references there is always another reference, you're
Mm.
effectively excluding the fact these sets where you have before pi and after pi, because now that reference does not exist because the on is impossible. So while we're reasoning with references and relationship between references, and you want the order to be this non-dense, sorry, that you can always put something in between in the ordering of your references, then you automatically get the reals. You don't get the rationals.
Is there
Because
any?
for the rationals, you would need to be able to say, sometimes I can put a reference in between, and sometimes I cannot put a reference in between.
So is there a sensible topology on the rationals at all?
So here's the thing. If this is what it boils down to physically. If you have a quantity that you're measuring with with notches, something before and something after, you can't know with this method whether you have rationals or reals.
Mm-hmm.
You really can't, because you would have to know infinite precision, which you can't. You know that you have a rational when you have a quantity that is defined as a ratio between two integers. But if you know that the quantity is defined as a ratio of two integers and you can measure the integers, you have measured the rational with infinite precision, which is completely different than measuring the real valued approximation of the rational.
Yeah.
So, in a sense, if you can define rationals and you can, the way that you measure rational would be completely different.
Yeah.
And if you are measuring rationals through their, let's say, digit approximation, like you're measuring with the boundary, that's when you're using the topology, let's say, of the reals, the order topology, to measure the rational, and that's when you would have the topology of the rationals. But if you're measuring the the numerator and the denominator, you don't have the topology of the reals. You have the discrete topology, because everything can be measured perfectly.
Yep.
And it's still fine because they're countable, and so you have a discrete topology on the countable. Everything is decidable, and you're still second countable and everything.
Mm-hmm.
So again, this is one of the also things of doing, physical mathematics, that you can go and see all these different topologies and see their meaning, and there is actually, you're doing. If you change topology, you're basically saying, I have these things and I'm measuring it this way.
Hmm.
Yes, as Alina says, rational and reals are equivalent under, if you're measuring it as with references like that, then you can't even tell that you have a rational. So you might as well say that you have a real, because you can't exclude the rationals like that. I'll give, if there is question from the chat, please put them now, because there is a delay, so I'm gonna lose them. And if there is nothing in 30 seconds, then we can close. And then next time we basically look at these discrete and continuous quantities, and then I think we basically are done with the parts that are done in the book.
Is there like any physical system where you'd want to use rationals and not reals? Like where that difference will be important?
Say it again.
like if there's any physical system where you would want to use rationals and not reals for your measurements, like if that difference will ever be important.
I mean, as I said, like if you have a quantity like I don't know, there is a population of people, right? So that's a finite number, and then you have chickens, and you want to say how many chickens do I have per person? That's a rational quantity, right? It's defined as a rational quantity because it is the ratio of two things. So
Yeah,
if
but
you
it's contingently defined as a rational quantity. I mean, you can say like 3 chickens per person, but you could also say 3.1 chickens per person or 3.14 chickens per person. There's nothing forbidding you from doing that. It just may be that you do not have sufficient resolution to measure that given the number of chickens and the number of persons you have. Um,
So this is where the quantity, you know that it's a rational because it's a ratio between two integers. And then if you measure the chicken and if you measure the person, then you're measuring the rational quantity. So you would have an integer topology. But if you are able, the way that you're measuring is that you have the amount of chicken for each person, and you're trying to measure what the amount of chicken for each person is, then you would be measuring the sort of the fractional approximation.
yeah.
Right? And you can imagine in economics, for example, right, that in principle, everything in economics is natural numbers, and then, well, integers, because you also have that. And then, any ratio that you can make is in principle, rational numbers. But then the way that you measure them is with approximations, and so you would have the topology of the reals. I
Mm.
don't think it plays any like important role, the fact that you have reals instead of rational instead of integers. There are some things in dynamical systems where it matters, and in chemistry it also matters, right? That the things are rational instead of the proportions are rational instead of reals. Uh, and in fact, you can measure things differently in chemistry as well. Like if you were able to make a molecule by molecule composition and see what happens, then you would be actually measuring it with integers. But if you are measuring moles and so on of Avogadro's numbers, then there would be approximations, and then again you would be measuring with the topology, with the order topology on the irrationals.
Yeah, I guess like it will be the same kind of thing as the chickens per persons for chemistry. So
Yeah,
technically, some concentrations are impossible.
yeah,
Um, but when
yeah.
you have like a really, 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 really large number of particles, it's effectively not the case. Uh,
Yeah.
and yeah, it will still be an approximation. So it's, yeah.
Yeah. It sort of works so that most of the time in chemistry you have like simple fractions, right? And so once you see that your data is 0.4999, you say it's gonna be a half, right? But in principle, if the ratios would be much more complicated, then you would have a problem.
Yeah. I mean, if you do take it to the limit, like if you go to infinite particles, technically you could go to any real, right?
Yes, yes. But then again, physically you can't, and so you
Yeah.
always have, yeah. So a couple of comments from the chat. Can valid. So the sessions are scheduled. We meet at 9 Eastern, US Eastern time. So basically, we started an hour and 10 minutes ago, and it's always the same. And then there is Julius with a couple of comments. I remember that millikan existence of electron was proven because charges of oil droplets were changing by an integer. Although the measure did not assume rational charges, measurement used reals. Yeah. It happened It just happened that the changes were very nicely ordered like integer, but initial model used reals. So only after the fact we can justify work with natural numbers of electrons. Yeah, yes, exactly. So you're measuring the reals, and then at some point, oh, look, this quantity fit nicely in a pattern, and then you say, okay, these are quantized. And information entropy is defined on a distribution, so it's already defined on an infinite collection, and therefore it's gonna be using real numbers always. Okay, if there are no other comments, we'll stop, and we'll see you next week. I don't think, let me check my schedule to see if I have any conflict, but I don't think so. Yeah, I don't have anything. So next week. Bye, everybody.
Bye. See you next week.
There we go.